All right, folks. This is our last lecture video. Stealing happy hours. Okay, let's get into it. Or I could just jam out to 311 all day. Okay, let's get it going. All right. I love me some 311. Back in the day in the 90s when the world was a lot less complicated than it is now. Okay, so picking up on this colligative properties, okay? So what we have going on, so I'm just making sure my stopwatch is ready. So I talked about this at the very end of the video, these colligative properties, okay? And so what we see here is the more of these things we add to solution, the bigger effect there is. That's what makes it a colligative property, okay? And so I'm going to show you here with respect to boiling point elevation and freezing point depression, there's a pretty cool way that we can actually see what we expect to happen with boiling point elevation or freezing point depression. So for example, I showed you that vapor pressure, when we add non-volatile solutes, it lowers the vapor pressure. Well, why is that? Well, that's because, recall, in the previous section, we talked about these hydrated ions, right? How in an aqueous solution, cations are surrounded by the negative end of oxygen, and anions are surrounded by the positive end of hydrogen. And that represents the strongest intermolecular forces, even stronger than hydrogen bonding. And so what this does is the presence of these ions makes it more difficult for water to evaporate and then eventually boil. It also makes it more difficult for water to freeze and crystallize into a solid. So what we observe now, if we look at this phase diagram, here is my triple point of pure water, okay? And if we follow this line here, this line is pure water, right? Well, you notice at any data point here, the vapor pressure of this pure water is lowered when we make an aqueous solution, when we put dissolved solutes in there, okay? And the prediction now is if we follow this vapor pressure curve all the way up to 1 atm, right, which is where we expect boiling to be. So here you can see this would be the boiling point of pure water, which would be 100.0 degrees Celsius, right? But now what you can see, because the vapor pressure has been lowered for the pure solvent, now the new boiling point of the aqueous solution has increased, okay? Subsequently, if we go back the other way now, right? Now what you notice here is because the presence of those solutes makes it more difficult for water molecules to find other water molecules and crystallize as a solid, we call that freezing, then this aqueous solution can exist as a liquid at lower temperatures, okay? So for example, we note here that if I go up now to the 1 atm to find the normal freezing point, here is my normal freezing point at 1 atmosphere of water, 0.0 degrees Celsius. And now what you can see for the solution is going to have a lower freezing point because the presence of these dissolved solutes disrupts the hydrogen bonding network, okay? So that's kind of explaining conceptually what's going on. Now in this video, I will show you how we can do calculations to predict the boiling point elevation, the freezing point depression, and we're also going to talk about osmosis at the end, okay?